Okay, let's dive into a research paper today. We're looking at a pretty fundamental challenge for AI models, especially, the ones that handle language.
Right. The problem of dealing with really, really long streams of information. Like, think processing an entire novel or maybe years of chat history.
Or a huge code base. Stuff that standard models can struggle with.
Yeah, models like transformers, which are everywhere now, their core attention mechanism, how they figure out context, it just gets incredibly expensive computationally as the sequence gets longer.
It's like comparing every single word to every other word.
Sort of, yeah. That's the intuition. And if you have thousands or tens of thousands of words,
That comparison task just balloons.
it really does. The compute cost, it grows quadratically. So if the sequence length is t, the cost is roughly t squared.
T squared, okay.
And memory use grows linearly with t, which is also a big deal. For short stuff, it's fine. But scale it up, and you hit a performance wall pretty fast. Too slow, too much memory needed.
Which is why people are looking for other ways, right? More efficient methods.
Definitely. There's been a lot of work on alternatives, like linear attention models, and more recently, things like state space models, or SSMs. Mamba is one people might know.
And these promise better scaling.
They do. They aim for linear time complexity, so OT,
Mm-hmm.
and sometimes even constant memory, O1, per step during inference, which is a huge theoretical win.
Okay, constant memory sounds amazing, but there must be a trade-off somewhere.
Well, the paper we're looking at highlights one. To get that O1 memory, these models often compress the entire sequence history into a single fixed-size state.
Ah, so you're squishing potentially vast amounts of context into one small box.
Kind of, yeah. And while that's super efficient, that fixed-size representation can struggle sometimes. It might lose the ability to perfectly recall specific details from way back in the sequence.
Like trying to remember the first chapter when you're on the last page using only a single sticky note summary.
That's a decent analogy.
Yeah.
So compared to standard attention, which can look back accurately but is slow, these efficient models might lose some fine-grained, long-range recall power.
So it's a spectrum. Powerful but slow standard attention on one end, fast but potentially lossy linear models on the other.
That's the landscape. And this is where the paper introduces its idea, log linear attention. It's trying to find a better balance.
Okay, log linear attention, a middle ground.
That seems to be the aim. Better long-range memory than the purely linear O1 state models, but still much, much more efficient than the quadratic cost of standard attention.
How does it do that? What's the core difference?
Instead of that single fixed-size state, log linear attention uses a set of hidden states to represent the past.
A set. Okay.
And the key is how many states are in that set. It grows logarithmically with the sequence length. So a log t.
Logarithmically, it's not fixed, but growing much, much slower than linearly.
Way slower. Think about it. Log base 2 of 1,000 is about 10. Log base 2 of the million is only about 20. It increases incredibly slowly compared to t itself, let alone t squared.
Right. So as the sequence gets massively longer, the memory needed for context only creeps up a tiny bit.
That's the idea. And the hypothesis is that this small, logarithmically growing set of states, if structured well, can hold on to long-range context much better than a single fixed state.
While still being manageable, computationally speaking.
Right. Still vastly more efficient than standard attention for those really long inputs.
Okay, so how is this memory actually structured? You said O log T states. How are they organized?
The paper takes this interesting view, framing many efficient attention mechanisms through a kind of masking lens. You have the standard attention calculation, and efficient methods apply a sort of mask to limit what each token can attend to.
A mask, like a filter.
Yeah, deciding which parts of the past are visible. Log linear attention introduces a specific kind of mask, one that creates a hierarchical structure for the memory.
Hierarchical, okay, like levels.
A bit like that. They use a partitioning method based on something called a Fenwick tree. It's a data structure. But here it's used to divide the history leading up to the current token into a specific set of buckets or partitions.
Buckets of history, and that gives you the logarithmic part.
Yes. Because of the way the Fenwick tree divides things up, each position in the sequence ends up attending to only a logarithmic number of these historical buckets.
So not one summary, but log T summaries.
Right. And importantly, these buckets represent the past at different scales, different levels of granularity.
Ah, so maybe one bucket for the very recent past, another for a slightly older chunk, and maybe bigger, coarser chunks further back.
That's the structure the Fenwick tree partitioning naturally creates. You get fine-grained memory for recent stuff and progressively coarser summaries for older context. which kind of aligns with intuition. Recent context often matters most, but you still need some signal from further back.
Makes sense. Does the model just treat all these buckets equally?
No, there's adaptability built in. Each bucket or level in this hierarchy gets a weight, and these weights are learned, they're data dependent.
Meaning the model figures out how much to pay attention to each timescale?
Right. Based on the current input, it can dynamically decide, okay, for this prediction, the short-term bucket is really important, or maybe I need to pull more from that medium-term summary.
That sounds flexible. Let's talk efficiency again. How does this O log T structure play out in practice? For inference, say.
When generating output token by token decoding, this structure means the memory footprint per step only grows as O log T, and the computation time per step is also O log T, which is great for generating long sequences without running out of steam.
Big improvement over linear growth in memory or quadratic compute. What about training the model? That usually involves parallel processing.
They show it works well there too. Using a parallel algorithm technique they call chunk scan, which processes the sequence in chunks, they can train these models efficiently. The compute cost for training becomes OIT log T.
T log T, still way better than T squared.
Definitely. And the memory needed during training is OP, linear. So significant savings compared to standard attention training, especially for long T.
What's also neat is that this isn't presented as just one specific new model, right? It's framed more generally.
It is. They position log linear attention as a mechanism, a kind of enhancement you can potentially add to existing efficient attention models.
So you could take something like Mamba-2 or another model, gated DeltaNet, I think they mentioned, and apply this log linear idea on top.
That's what they demonstrate. Conceptually, you can think of the original model having its own attention pattern or mask, let's call it MS. The log linear approach introduces this hierarchical mask, MH.
And you combine them.
You effectively compose them.
Yeah.
The resulting attention pattern benefits from both the original model structure and the new hierarchical logarithmic memory structure. It's a way to potentially boost the long-range capabilities of already efficient models.
Okay, the theory sounds solid. The mechanism is clever. Does it hold up when tested? What did the experiments show?
They ran a bunch of tests. One was a synthetic benchmark called MQAR, multi-query associative recall. It's specifically designed to test if a model can find and recall specific pieces of information stored far back in a sequence.
A direct test of that long-range memory claim.
Right. And they found that their log linear version of gated DeltaNet maintained really high accuracy on this task, even as the sequences got very long.
And the baseline linear version.
Its performance dropped off noticeably on the longer sequences. So this was pretty clear evidence that the log linear structure was helping with that specific kind of long-distance recall.
What about more standard tasks, like just predicting the next word in normal text, language modeling perplexity, and things like that?
On those benchmarks, using datasets like Wikitext, the log linear versions generally performed about the same as, or sometimes slightly better than, their linear-based models.
That's important too. You don't want to gain long-range ability but lose performance on standard tasks.
For sure. And they noted that log linear gated DeltaNet actually performed quite strongly here, sometimes even doing a bit better than some transformer baselines on those perplexity scores.
Did they look inside the long sequences? Like, how well does it predict a word deep inside a text, using all the context before it?
Yes, they did what's called a per-position loss analysis, basically checking the prediction error for tokens at different points in a long sequence.
And if it's using long context well,
its error should decrease as it sees more and more preceding context, even for tokens far into the sequence. And that's what they saw. The log linear models consistently had lower prediction loss across various positions in long sequences compared to the linear ones.
suggesting they really are leveraging that long-range information better.
Seems like strong evidence for it.
Okay, what about those needle in a haystack tests? Finding specific facts buried in long documents.
Another benchmark they used. Here, you hide a specific fact, the needle, deep inside a lot of irrelevant text, the haystack, and ask the model a question that requires finding that needle.
A classic long context challenge.
Yep. And the log linear versions generally showed better performance here too, compared to the base linear models, especially in harder versions where they had to find multiple needles scattered throughout the text.
So, across synthetic tests, language modeling, internal analysis, and retrieval tasks, the pattern seems consistent.
The results point towards the log linear approach effectively improving long-range capabilities compared to the linear baselines it was built upon. It seems to deliver on that promise of better recall over distance.
Let's bring this back to you, the listener. We're doing this deep dive to help you get informed quickly. So why does cracking this long context problem matter?
Well, think about current AI limitations. Often, you can only feed a model so much text at once, right? You might have to summarize long documents piece by piece.
Or a chatbot might forget the start of a long conversation. You can't just give it your entire research library or years of emails and expect it to synthesize everything perfectly.
Right. The ability for AI to truly process and understand very long sequences, whole books, complex legal cases, massive code repositories, is currently hampered by these computational bottlenecks we've discussed.
And log linear attention is presented as a step towards overcoming that.
Exactly. It's aiming to build models that can handle much larger amounts of information without the performance just falling off a cliff. And crucially, without losing the ability to connect the dots or recall specific details from way back.
Which could unlock new ways for AI to help us analyze, understand, and generate information based on much richer, longer contexts. That seems like a pretty significant potential shift.
It's definitely a promising area of research.
Yeah.
Now, the paper is also careful to point out this isn't a silver bullet. There are nuances.
Okay, what are some of the limitations or caveats mentioned?
Well, first, it didn't improve performance on absolutely every single task or metric. While strong on long context, its benefits weren't universal across all tests they ran.
And how does it stack up against the original heavyweight standard attention?
There's still often a performance gap compared to full transformers on some standard benchmarks. The trade-off is, of course, the massive efficiency gain of log linear versus quadratic. But transformers can still be top performers if you can afford the compute.
And implementing this isn't trivial.
They note it's more complex than a simple linear attention model. You need to handle the hierarchical structure, the Fenwick tree logic, the chunk scan parallelism. It requires more careful engineering.
What about the specific structure they chose, that Fenwick tree approach?
They mention that this specific partitioning introduces a particular kind of inductive bias. It naturally prioritizes recent context more heavily. While that seems sensible for many tasks, it might not be the absolute best structure for every possible type of long sequence problem. There might be other ways to build useful hierarchical memories.
So a solid step forward, particularly for long context tasks, building cleverly on prior work but still part of the ongoing research journey.
That sums it up well. Log linear attention is a really interesting approach. It uses these hierarchical memory structures, growing that memory logarithmically, O log t, to try and find that sweet spot between the efficiency of linear models and the power of standard attention.
And the evidence suggests it makes real headway, especially on tasks that demand understanding over long distances.
Yes, it offers a compelling direction for building models that can finally start to grapple effectively with the truly long sequences of information we encounter all the time.
So as we wrap up, here's something to think about. If AI models get significantly better at processing and understanding vast streams of information far beyond today's limits, how could that change how you interact with technology? What new possibilities open up when AI can truly comprehend the long view?